We do have some fantastic questions online, and also any questions in the audience, do raise your hand in the traditional manner, and my colleague Katie will be round with you with a microphone. So if there's anyone here, but while we're waiting, I can give you a few from online that we've had already. I think there's someone just at the back there, Katie. So there's an interesting little discussion about red shifting and blue shifting. So someone said, well, could you have blue shifting as well? And other people in the chat, who I don't know if they're astronomers or not, said, well, surely the Andromeda galaxy might be blue shifting because it's coming towards us rather than moving away from us. And then someone else said, but then surely then you have to work out, if you're working out the redshift, then there's going to be a combination between the general expansion of the universe following the Big Bang, but also is that galaxy or whatever moving towards us, and so how do you work all of that out, basically?
So yeah, you are absolutely right. So astronomers call there are two kinds of motions that galaxies can have in the universe. There are the motions of individual galaxies moving around in the way that the Milky Way is coming towards us, and there's the motion caused by the grand expansion of the universe. And for very, very nearby things, it can get confusing. So the Andromeda galaxy is actually coming towards us, even though the universe is expanding. What happens, the reason that everything distant is moving away from us is because galaxies on average are all roughly moving around at the same speed. 100 kilometers per second or a couple of 100 kilometers per second, that's the average amount that galaxies are flying around the universe. The expansion speed of the universe just gets bigger and bigger and bigger and bigger with distance, because all space expands at an equal rate. And so if you have something 10 times further away, that 10 times more space is expanding equally, and so you have 10 times more speed, right? And so the more and more and more and more distant you go, the recession speed, because of the expansion of the universe, gets bigger and bigger and bigger. And so to work out the combined total speed, you add the two things together. So you add together the wiggling around motion and the expansion speed due to the universe. And for very, very nearby things, the expansion speed of the universe is very, very small, and the expansion and the speed of the galaxy is just moving around is very, very big. And so the overall effect can be the galaxy moving towards us. For something that's very, very far away, the expansion speed of the universe might be 100 times faster than any galaxy could go. And so even if a galaxy is trying to go towards us, it's being pushed away 100 times faster by the expansion of the universe. So nearby things can be blue shifted, but in general, everything else is traveling away from us.
That makes sense. Did I see a question here? There's a question there at the front, Katie. Also, if you're up in the gallery, it's quite bright on stage, so do wave furiously, and I will try and make you out. Question here, thanks.
Thanks. Could you say a bit more about what the James Webb Telescope is doing in terms of, is it resolving or solving this resolution problem you were talking about being able to see these galaxies in sort of more detail?
Right, so the James Webb unfortunately won't solve the resolution problem. So the way to get better resolution in astronomy is to either build bigger and bigger and bigger mirrors, bigger and bigger telescopes, or use lots of telescopes linked up together. So the James Webb Telescope has a big mirror, about 6.5 meters across, but that's still not big enough to solve the blobby problem. What it's going to do, it's going to be more sensitive than any other telescope, and it's going to be able to get measurements at wavelengths we've never been able to measure these things at before. So it's what we call the near and the mid infrared, and so it's going to be able to see light from newborn stars and old stars and the hot dust around these star formation regions. So it's less about taking pictures of them and more just getting all the information about how the stars are forming and using that to inform our model, if that makes sense. So yes, probably no pretty pictures, but definitely loads of great information that will let us understand these things.
In fact, someone online was asking, what resolution, do you know, will it be able to give us images at?
Well, it depends on the wavelength, of course. So as so there's an equation, right? So as your mirror gets bigger, your resolution gets better. As your wavelength gets longer, your resolution gets worse. And so James Webb is going to be able to see across quite a long range of wavelengths. So pretty good resolution in the short wavelengths, and then getting systematically worse as you go to longer and longer wavelengths. But definitely significantly better than Hubble in the short wavelengths.
Excellent. I was just thinking, by the way, it's a real shame that we got this lovely bulb out and you'd set up all this experiment,
and then my computer
and then your computer just decided to say,
I'm sorry.
Oh, I don't think so. Ross, I don't know if you could come down here and just have a fiddle, because it would just be great to see this thing work. And we have one of our directors from the mid-20th century, Lawrence Bragg. He had a phrase which is, don't tell people about science, show them science. And so I'd really like to get this working if we could.
Yeah.
So I'll just let Ross have a bit of a fiddle with your laptop while we take a few questions, if that's okay.
Yeah, sure.
Because it's just a really cool little demo that just illustrates your point really nicely. And it's just a shame. It's just a shame it didn't work. But while I'm here, I'll just give you another question, which is. Well, you've talked a lot, and this is a question from Dina actually, talks a lot about dust, and this is dust, and these are pillars of dust. But what is dust in that sense? I mean, when I think of dust around my house, I mean, we're told that's human skin and other dead, horrible things.
Yeah.
So I'm doubting it's that, but what is it actually chemically? Is it just rocks or what?
No, so it's not. So dust is probably a terrible name for it, to be honest. It's probably best to think of it as being more like smoke than anything else. So it's tiny, tiny particles of heavy elements. And so when astronomers say heavy elements, we basically mean anything that's not hydrogen or helium. And dust is made by stars, right? So stars, this is a very long answer, but stars live their lives and they burn hydrogen and they produce these heavier and heavier elements. And then when they die, they explode and they shower the universe with these heavy elements, things like carbon and oxygen and iron. And these heavy elements can form just little molecules that float around, and that's dust. So it's much, 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 much smaller than the dust that we have in our house. And it's just a sea of smoke made of dead stars, basically.
But even smaller than smoke particles, like literally individual molecules sort of size?
Well, they can be. So often almost exactly identical to smoke particles, actually. So a lot of dust particles are what we call PAHs, polycyclic aromatic hydrocarbons. And you get those things in smoke as well. There's an amazing astronomy graph I've seen of a spectrum of the Orion star-forming nebula and the spectrum of a car exhaust. And they match exactly because you have the same particles in each. It's all the same stuff, right? It's just some of it's here on Earth and some of it's out in the universe.
And the fact that the stuff in the universe is much, much colder doesn't affect, it's still just...
So it can affect it, but in terms of what we call in terms of the wavelengths the molecules give out, no, that's always the same. The same molecules will always give out the same wavelengths.
Ross is shaking his head. He's not happy.
That's a bad
well. You'll have to come and watch it on the screen afterwards for those of you that are here. There's a question at the front here, Katie, and then a few towards the back as well. Once we're and I'm on there as well.
Is the universe expanding and getting quicker or slowing down?
That's a really good question that we discovered the answer to in the late 1990s. So when I was growing up, we thought the answer was that it was slowing down because gravity likes to pull things together. And so we figured, okay, there's all this stuff in the universe, the gravity of all the stuff will be pulling it back together. And so they designed an experiment to measure how quickly it was being pulled, the expansion was slowing down, to try and work out how far in the future it would all get pulled back together for a crunch. And in one of the biggest scientific surprises of all time, it turns out the universe expansion is speeding up. There is something in the universe pushing it apart faster and faster and faster, and we have no idea what it is. We call it dark energy. So dark energy is the name for this effect that we see. But astronomers sometimes use the word dark to mean I have no idea what's going on here. So it's more the name for an effect than anything else. So it is speeding up, and it's speeding up because of this stuff that we call dark energy. And as for how that actually works, we're still working on it.
I thought I saw a hand up in the gallery, but it might have just been someone stretching. So apologies for that. You'll have to come back down again, Katie, I'm afraid. So get your steps in. While Katie's making her way back down to take some questions from the theatre, there was another question here, which is from Shafak, who said, why should the electromagnetic spectrum be continuous? I mean, you said that obviously Newton saw some sort of gaps in the spectrum of sunlight. Was it Newton or was it Herschel? I can't remember.
So carry with the question.
But just if photons are a quanta of light, then shouldn't there be some quantization of the spectrum, and shouldn't we actually be a lot of separate lines, or is that not true? Is it actually?
So we actually do see spectra being quantized. If you look at the spectrum of the sun, for example, there is a forest of dark lines in the spectrum of the sun, and that's caused by all the different species of atoms and molecules inside the sun. That's actually how astronomers work out what pretty much everything is made of. If you went back a couple of hundred years and asked people if we would ever know what the stars were made of, they would think that was a ridiculous ridiculous idea. Now we know with amazing accuracy what distant stars and galaxies are made of, and it's because of these lines in the spectra. So individual atoms and individual molecules have very characteristic fingerprint lines that we can spot in distant objects. So yeah, in some way, the spectrum kind of does have these features in.
But if I had just like the purest white light going through my prism, would I still see lines and gaps in there, or is it impossible to get pure white light?
I think you might have to ask a quantum physicist. I'm not sure. I think maybe if you zoom in very, 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 very far beyond all possible technology, then perhaps energy levels are quantized. But yes, you might have to ask a quantum physicist. I think that's
fair enough. Sorry for making you run around there, Keith. There was a question in the red there. Thank you.
I was going back to your paleontology analogy.
Oh, sure.
Have you looked back in time at different intervals to look for the missing link between the sub-millimeter galaxies and the red and dead galaxies?
Yeah, we absolutely have. So the latest surveys in astronomy are really, really good at studying galaxies across all cosmic time. And so we can watch these galaxies grow and evolve and then die and then evolve down towards the present day. So it's by doing that we figured out what kills these galaxies, which is something I didn't mention. As far as we can tell, they're killed by their black holes. So every big galaxy has a supermassive black hole in the center, and at some point in the evolution of these galaxies, a bit later than the ones I was showing today, the black hole kind of wakes up and devastates the galaxy around it and blows away all the gas, and then the galaxy stops forming stars and dies. So that happens a bit later on. So yeah, we do have these surveys. We call them pencil beam surveys because we take this very small patch of sky and just go further and further and further and further out, and that's like a slice back across through the universe's history, and we can tell the entire story.
And there's a question there.
You said that there was the sub-millimeter light on the red side of the spectrum. Is there something similar on the blue side or the violet side? Another candidate for seeing.
So yes, there absolutely is. So there's so much in the spectrum. So what I was talking about today is just one story from one small part of the spectrum. If I go back to this. So on the blue side of the spectrum, we come across, first of all, ultraviolet. And then if we go even further, we hit X-rays, which are the X-rays that you get in a hospital that can see through your body. And then if we go even further beyond X-rays, we reach gamma rays, which are some of the highest energy lights that we've ever found in the universe. So that there's so much across the spectrum. And the amazing thing is that when you look at these different types of lights and use these different types of light to study the universe, you see something completely different every time. Like the universe, as we look at it in radio waves, looks completely different to the universe as we look at it in gamma rays. So gamma rays and X-rays are really good for seeing black holes, for example, which is like a whole other story.
There's another question?
If the universe is expanding and the expansion is accelerating, at what point, according to relativity, nothing can travel faster than the speed of light, but can space expand faster than the speed of light? Because surely, at some point, if the expansion is accelerating, it will reach that point soon?
Yeah, so you are absolutely right. So the expansion can very easily be faster than the speed of light. And in fact, most of the galaxies I was talking about today are probably receding from us faster than the speed of light, which sounds kind of bonkers, right? It sounds like it breaks relativity. The answer is that the expansion of the universe isn't a movement through space. So the relativity limit, it says that things can't travel through space faster than the speed of light. Like if you throw a ball, that's traveling through space, that can't travel faster than the speed of light. But the expansion of the universe isn't stuff moving through space, it's space itself growing, right? It's space itself expanding. And so you're not moving through space, space itself is carrying you along. An analogy might be, imagine if you're at the airport and you're driving one of those like little motorized car things, and say they have a fixed speed limit of 10 miles an hour or something. If you drive onto the motorized walkway, you could leave your friend behind way faster than 10 miles an hour because the motorized walkway is carrying you off, right? You're not breaking the speed limit of your car, it's the floor itself is carrying you away. And that's that's the way the universe works. So the space itself, as far as we can tell, there's no limit to how fast it can expand.
There's actually a question online that kind of links to this, which is, are we seeing, therefore, less and less universe, and could there be a time in the future? I think Katie Mack talks about this in her book, The End of Everything. So therefore, there might, if the universe gets so far away and so big, and like you say, it's maybe even going faster than speed of light, or, you know, out there, could we therefore end up in a little pocket of universe and never actually be able to see things that are so far away that the light wouldn't be able to travel? Do you see what I mean? We might end up on our own little island of visible universe.
It's quite depressing, but I think the answer is almost inevitably yes. So there is the cosmic horizon, so that's about 46.5 billion light years to the edge. And that is a true horizon. We can't see anything further away than 46.5 billion light years. And that's because anything further away than that, the light just hasn't had time to reach us yet. But because the expansion of the universe is speeding up, more and more and more things are going to drop over the cosmic horizon. So it could well be in the far, far, far distant future, you know, quadrillions of years in the future, we could not know about anything apart from our own galaxy. Which I think is almost a tragedy, because if you think about, not only because of how much we know about the universe, but all of our knowledge of the Big Bang. We know that our universe started with a Big Bang because we can study the echo of the Big Bang, we can see other galaxies moving away from us. If we end up trapped in our little pockets, you know, future astronomers might not even know that our universe is expanding at all, because all the evidence is over the horizon. It's a reason to be cheerful, right? We're very, you know, we're living at the time that we can learn about our universe. It's amazing.
Well, let's hope we write it down so future astronomers can know what we knew. Yeah, it's baffling to think on those timescales in terms of passing on knowledge. There's a question here.
So kind of taking that one step further, what might we be able to see with gravity waves?
So the answer is, gravity, so for anyone that doesn't know, so gravitational waves are these ripples in space and time that were predicted by Einstein about a century ago, and we only discovered them for the first time. We got, you know, real evidence for them here on Earth about 6 years ago. So everything that accelerates produces gravity waves. Like if I wave my hand, like I'm making gravity waves right now, but just pretty puny ones that you could never see. So far, our gravity wave detectors can detect really, really big things, really shaking up space and time. So think like neutron stars crashing together or black holes crashing together. And so the first gravitational wave that was detected was the collision of two black holes. And we've since discovered, neutron stars crashing together and all kinds of things. In terms of the science that we're doing, we're already learning more about how black holes work. For example, there was always this gap. We knew about supermassive black holes, and we knew about regular black holes that were formed from stars, but we thought there was a gap in the middle. And by using gravitational waves, we've discovered our cosmic missing link. We've discovered an intermediate mass black hole between a supermassive one and a regular one. And again, without gravity waves, we would have never have found this thing. And gravitational waves they're still in their infancy. We've only been doing gravitational wave science for like 6 years now. We are going to go to space and detect very, very big gravitational waves and discover all kinds of things. So I think it's going to be a gravitational wave century, I think.
Just while Katie makes, I think there was a question over here, is that right? While Katie makes a way, I'll just take a question from Layla, who's 9, watching online, who says, how many stars are there in the universe?
One of those easy questions, So the answer is there are maybe a million stars, maybe a million stars in the galaxy. That's probably on the high side. And there are at least a million galaxies in the universe that we can see. So somewhere around a million stars in the universe, which for reference is more than there are grains of sand on every beach in the world, which is another one of those facts that just sort of makes my head fall off a bit. But yeah, the answer is a lot, is the quick answer.
I mean, it's kind of crazy that there's as many stars in the galaxy as there are galaxies in the universe.
That's only in the observable universe, right? That's our 46.5 billion light year bubble that we're trapped in. I mean, beyond that, it might be infinite. We just don't know.
Well, at least, you're not, as an astronomer, there's still going to be plenty to look at.
Well, exactly. Like, we're always going to have jobs, right?
There's a question there.
Yeah, are gravitational waves part of the electromagnetic spectrum? And if they're not, how do they actually... We know how the electromagnetic spectrum goes through space. How do they go through space?
So the quick answer is no. So gravitational waves are not part of the electromagnetic spectrum. They are ripples in space and time itself. So Newton's idea of gravity was that gravity was this mysterious force that pulled on things, right? That's not true. So Einstein's big breakthrough was that what gravity is the bending and the stretching of space and time. So it sounds pretty crazy, but apparently it's true. So the space-time itself is this bendy, stretchy, flexible fabric. And the more bent and stretched it is, the more gravity, like we feel. And so if space-time is this bendy, stretchy fabric, then you can imagine how it can have waves in it, like waves on a trampoline or something. And so electromagnetism are waves of energy inside the universe. Gravitational waves are waves of the universe itself. And so this bendy, stretchy space-time fabric can just propagate waves outwards.
So there's a couple of questions again on black holes, which is how do those supermassive black holes that you said are the center of the galaxy, how do they form? Do we know, or do we?
Right, so that's actually one of the, that's what we call an open question in astronomy, which is I'm saying I don't know. So there are a few different theories. So we think the first stars in the universe that formed were very, very big, much bigger than ordinary stars. And so when normal black holes die, when stars explode and they leave behind black holes, the first stars in the universe might have been 10,000 times bigger than the sun. And so if one of those giant stars died, it might have left behind a very, very, very big black hole. And then if you get enough black holes that weigh 10,000 times as much as the sun and you smush them together, you can make a black hole that weighs millions of times as much as the sun. But the existence of these very, very massive stars is kind of theoretical. So we think it might have something to do with black holes merging together to make bigger black holes. But we're only at the start of our understanding of this through gravitational waves. So it was 2015 we were able to spot the first ever black hole merger. So we think that's got something to do with it. But actually how it works, we are still working on it.
So you've actually sort of answered another question, which is what happens when black holes crash into each other? And I think the answer is we get a gravity wave, and we can
get a gravity wave and an enormous amount of energy. One of my favorite astronomy facts: the 2015 black hole merger that caused the gravitational wave that we detected. In the last fraction of a second, when the two black holes came together, it released more energy than every single star in the observable universe put together. In that moment, just this one event, every single star is unbelievable. So you get when two black holes crash together, you get a slightly bigger black hole and an unfathomable amount of energy.
Wow! And does that show up in in some of these spectrums as well, or is it so far away we wouldn't be able to see it?
It can do. So when, I think it was in 2017, we discovered a black hole and a neutron star crashing together, and we detected it first in gravitational waves, but then as soon as we detected the gravitational waves, like the bat signal went out for astronomers to point their telescopes in this part of the sky, and we discovered the afterglow in the electromagnetic spectrum. That was the first time that gravitational waves and regular light have worked together to understand the universe.
And that's sort of, one of the futures of astronomy in a way, isn't it? To be able to put together these two different ways of sensing the universe.
Yeah, absolutely. And that happened over the last century with the electromagnetic spectrum. I think in the past it was possible to be maybe an infrared astronomer and you would just do your infrared astronomy and you wouldn't talk to anyone else. But the history of the 20th century is astronomers combining and using the entire power of the spectrum at once to understand the universe. And then, with gravitational waves, we're going to extend that. We're going to use all the information here and gravitational waves and neutrinos and all kinds of things, just paint this complete picture of what we see.
I believe you've got a question there, Katie? Oh, sorry, there's a question behind you, and then we'll come to you afterwards. Sorry.
What do you think it would look like to live on a planet inside one of these invisible galaxies? Because the night sky that you showed of what it looked like when Andromeda was coming to crash into us looked pretty amazing.
Yeah, it's a good question. So, first of all, these galaxies are very, very far in the past in the universe's history. And because they are so early, they don't have as many heavy elements as modern-day galaxies. Like the history of the universe starts off just totally made of hydrogen. And then over time, generations of stars live and die, and you build up these bigger and bigger and bigger like reservoirs of heavy elements. And heavy elements, things like carbon, silicon, oxygen, iron, that you can make planets from. So these galaxies are quite poor in these heavy elements, so you might not have enough to even form planets yet. Planets might be a feature of the late universe. Although they do have lots of dust in them, so maybe. I think I don't totally know the answer. I think the simple answer would be it would be amazing to see the night sky, right? I showed you those simulations of the Andromeda Galaxy crashing into the Milky Way. I think it would be like that on steroids. I think it would be a pretty remarkable view.
Fantastic. And a question here from this gentleman.
You talk about observing black holes merging or destroying each other, but are you observing in real time, albeit millions of light years later? Are these things taking place I don't know how long it takes to observe these things, but let's say it takes a month for this to collapse or whatever. Is that how long it takes for that to...
Well, it takes... I think your question was if you're talking about thousands of years later, that's the time it takes for the signal to travel, right? So, and yeah, that is right. That is the answer. So, just as we are seeing these sub-millimeter galaxies I was talking about, we're seeing them as they were, 10, 11, 12 billion years in the past. And the same is true of gravitational waves. So, gravitational waves travel at the speed of light. And so, the big collision we saw in 2015, the two black holes were crashing together about 1.5 billion light years away. Excuse me, and so the light would have taken the gravitational waves would have taken 1.5 billion years to reach us, and so we're seeing into the past, as with everything else in astronomy.
Actually takes the month.
Well, it depends what you call the actual collapse, right? So the black hole, they weren't just flying past and hitting each other. They started off as a binary black hole system. So the black holes would have been orbiting around each other for millions of years. And as they were radiating gravitational waves, they'd be getting spiraling in closer and closer and closer and closer and closer. The actual signal that we saw, the actual crash, lasted a fraction of a second. It was about 0.2 seconds or something was the actual crash together. But the lead up to the crash would have taken millions and millions of years. And they would have been radiating gravitational waves as well, but they would have been too small for us to notice. It's only the actual coming together, the crash, because our gravitational wave science is brand new. We can only discover the really, really big things, so we can see that 0.2 second crash.
Wow. So there's a phrase or a topic that you just kind of skirted over in your talk when you said, oh, and yeah, of course, there's a little bit of dark matter that just is around everything, that keeps everything together. And you just sort of you tried not to concentrate on that. But of course, that's going to come up, obviously, in the questions online, which is, do you think any of the James Webb or any of these other imaging technologies will help us identify dark matter, or is the fact that it's, pretty invisible, actually we won't be able to see it using James Webb or any of the sort of newer gravitational wave technologies or anything?
Right, so James Webb definitely won't see dark matter. So James Webb is not designed and it's not hoping to see dark matter. So dark matter is, of course, this invisible substance which permeates the entire universe and it holds galaxies together. And the slightly disturbing thing is that it outweighs the regular universe, something like 5 to 1. And if you add dark energy into the matter, so regular matter, which makes up me and you and the sun and all the stars in the sky, makes up 5% of the universe, like fully 95%, which is dark energy and dark matter. We don't know what it is. In terms of searching for dark matter, there are two different approaches. You can either go big and look at the whole universe, or you can go small and you can search for it right here on Earth. So we go big and we look at the whole universe and we can compare the universe we see to dark matter simulations, right? We can kind of make different models for how dark matter might behave, and then we ask the question, what kind of universe does this produce? If dark matter acts like this, what does the universe look like? And then we compare to the real universe, and then eventually we can get a good guess for what dark matter should be. And our best guess is that it's some tiny subatomic particle which interacts gravitationally but ignores electromagnetism. And because light is an electromagnetic wave, dark matter just completely ignores light. Of course, when we discover what it is, we won't call it dark matter, right? We'll just call it the kind of inverse lepton neutrino or whatever. We'll have some name for it. But for now, we think the universe is full of this mysterious little particle which ignores electromagnetism. So the way we're actually hunting for it is by going small here on Earth and building detectors to actually catch dark matter particles in action. And the way it's super cool the way they do this. They go underground and they normally build these dark matter detectors in old abandoned mines, and they build these big tanks of liquid and they wait for dark matter particles to just fly along and then ricochet into the nucleus of a waiting atom and cause a little spark. And then that's the detection that we're waiting to see. And we've been doing it for a very long time, and so far we've seen absolutely nothing. So it's a bit like trying to catch a mysterious fish and you're using a net, and then every year you go and make the holes in your net smaller and you just keep not seeing anything. So our detectors get more and more and more sensitive every year. So we're not panicking just yet. I think at some point, if we've eliminated all the types of dark matter that could be and we still haven't found anything, then we might get worried. But for a while, there's still places to look.
Casey, I believe you had someone with a question up here. Yeah.
Sorry, another question. Given what we know about the electromagnetic spectrum, including light, and also what we know about particle physics, why don't we know whether light is a particle or a wave?
That's such a good question. So I think you could talk for an hour just about this. So I think the actual answer is that light is neither a particle nor a wave. It's neither, right? Light is actually something pretty deeply mysterious that we don't understand. Being a particle and being a wave are two different models that we use to understand how light behaves. But like, models aren't reality, right? Models are our description of reality. And the answer is that light sometimes behaves like a wave, and it sometimes behaves as a particle. It sort of behaves like a wave when you're not looking at it, and then when you look at it, it behaves like a particle. But these models aren't the same as reality, right? So we have these two different descriptions of what light does. What it actually is underneath is something very, very deeply weird that we don't quite know how to get our heads around. But yeah, the best we can do is have these two different stories.
I think I saw another hand there. Is that right? No? Okay, fine. We've got a few more questions online, or anyone else? Oh, there's a question there as well in the audience.
Sorry, pass the mic.
Thanks. I really liked your metaphor of the 9 grand pianos. But looking at this, what stops you from going off the end and just saying, well, we'll add 10 times the wavelength by 10 and times it by 10 and times it by 10? There's no maximum number. So what stops you from reaching the end?
That's a really good point. So it's more of a practical limit than a theoretical limit. So yeah, in theory, there's no limit to how long wavelengths can be or how short wavelengths can be. So in theory, this goes off on either side forever. There's a practical limit in our universe, though. So on the high energy side, when you go to X-rays and gamma rays, you're going to higher and higher energies. After a while, you reach energies so high that there's nothing in our universe that could ever produce something that's energetic, so they just literally don't exist. And the same is true on the other side. You go to lower and lower energy, to bigger and bigger waves, and then eventually you reach a point where there's just nothing physically in our universe that can produce waves of that long wavelength. So it's a practical limit based on what our universe is made of more than anything else.
Thank you very much. It's probably just time for sort of one more question or two. I don't know if anyone here... Oh, there's a question at the back there. We'll go for that one. Actually, that question was exactly the one I was going to ask. Someone else had asked online, which is, can you get even more gamma than gamma and even more radio than radio? But yeah, that sort of answers the question.
If the gamma and X-ray is high energy, why is it colder on the thermometer?
That's always baffled me as well.
Okay. So it's a very good question, which I'm working out how to explain. So what the thermometer is measuring is what we call black body radiation, right? And these heat radiation, which what we feel as heat, is infrared at these wavelengths of kind of 10 or 20 microns. I think really the short answer is that in sunlight, like through the prism, like that Herschel was doing, sunlight doesn't have gamma rays and X-rays in it. They carry more energy, and I think maybe if you were to put a thermometer into a gamma ray producing machine, it might do some interesting things, but just there wasn't gamma rays and X-rays in the solar spectrum to produce that.